Last, we'll finish this chapter by an application to analysis. The Weierstrass approximation theorem says that every continuous real function on an interval can be uniformly approximated by a polynomial. I think a lot of you have seen it if you have taken real analysis course. And stated, it's very, very, very classic theorem, like proved in 18th century, 19th century. That f maps from 0 to 1 to real line be a continuous function. And let epsilon be a positive number. Then there is a polynomial px such that distance between px and fx is bounded by epsilon for all x in 0 to 1. And it's proved in last century, Bernstein proved gave a very probabilistic proof, which is very nice. And the idea is to approximate f by a sum of polynomials that look like bump, which means like this: a function p sub n x being the sum of all such eix times f to the I over n. Here, what is an eix? The eix is the probability of the binomial variable with parameter nx equals to I. And it equals to n choose I times x to the power of I times 1 minus x to the power of n minus I. And I ranges from 0 to n. And this ei is chosen as some polynomials peaks at x equal to I over n, and then decays away from x equal to 1 over n. And we can see that for each x in the range of 0 to 1, the binomial distribution has been nx and variance nx times 1 minus x, which is bounded by n. And then by Chebyshev inequality, we can see that the sum of all I such that I minus nx is greater than n to the power of 2 over 3, and the summation is e sub I to x, is the probability of distance of binomial nx minus nx is greater than n to the power of 2 over 3. This is bounded by n to the power of negative 1 over 3. And actually in the later on we see Chernoff span, we'll see a much better tail bound. And since 0 to 1, this closed set is compact, and f is uniformly continuous and bounded by some basic analysis by multiplying by constant. We assume that fx is bounded by 1 for all x in range of 0 to 1. Also, there exists delta, positive delta, such that fx and x minus xy is bounded by half epsilon for all xy in the range of 0 to 1, with x minus 1 bounded by delta. It's very basic analysis. Take n greater than the maximum of 64 epsilon to the power of -3, or epsilon to the power of -3, or delta to the power of -3. Then for every x in 0 to 1, we can notice that the sum of all ej x is 1. From the definition, you can see that. Then the probability of Pnx minus fx, we can bound them now. This is bounded by the sum of all eix times f to I over n minus fx. And this one is bounded by taking over summation, taking over all I, such that I over n minus x is bounded by n to the power of -1/3, which is smaller than delta. And the summation is over all eix times f I over n minus fx plus the I such that I minus nx is greater than n to the power of -2/3. We divide them into two, split them eix. This is less than equal than the first term is bounded by half epsilon, and the second term is bounded by 2 to the times n to the power of -1/3, which can be bounded by epsilon. Which complete our proof here. It's a very nice proof. It tells that our probabilistic method, especially the second moment method, can be applied in even analysis field.